Hi, it's Terry Dennery of the MathWorks. So, anyways, following up on our previous video, we kind of came up with a controller that sort of works on accelerating or basically bringing the propellers to a speed which will give the proper lift to essentially lift the full vehicle. All right. And we had a little bit of an issue that we corrected kind of through the general thought process of, well, we anticipate we're going to use much wider propellers than these steel ones that we're using right now, which have this massive material density of 77,850 kilograms per meter cubed. That we're going to use them anyways, and if we, just kind of arbitrarily. Well, I'd say that my problem with our choice was that it was too arbitrary, and we just said, well, we're going to use something wider, and perhaps 20. Dividing it by 20 is the answer. So, anyways, I want to kind of revisit that, and let's return it to its original material density. Right now, I already did that for the shaft on the propeller, and so with that, we're back to where we were. And so I'm going to just hit run, and it brings up the spinning propeller, and calculation's already done. And so we're back to the situation where we have quite a bit of oscillation at the beginning, right? And it's this that I'm saying is a problem, and there's some pretty smart fixes on how to do this. And the real problem, is this, initial thrust, just going straight to a non-zero value in this calculation. Well, it's very much in conflict with the initial condition of zero for the angular velocities of the propellers. And so it really means, well, let's just kind of ramp it up a little bit, right? And that this initial thrust is there, not because our trajectory is starting off at zero and saying the on the movement of the vehicle. It's that we're just saying compensate for gravity right off the bat. And I'd say that well, this thing can sit on the ground for a few seconds at least before it reaches a proper compensation for gravity. All right, and so I'm going to propose, let's spin them up over 8 seconds, and so therefore let's ramp up on the gold line, and it's not such a hard thing to do. And so this block's really good at defining ramps. And so I'm just going to repurpose it for doing gravity as well, right? And so basic idea is we're going to set a trajectory that begins at t equals 0. And over a 8-second period, we're going to go from 0 to that gravity constant. Okay. And so this will be the first, if you'll recall, PVA is a 3-component array. This will be the first term, and so we'll use this selector and put in a 1 right there to get that. And then that will join with the acceleration for our chosen trajectory to essentially set, multiply with mass to set the thrust requirement for each of our propulsion units, right? And so let's go back here and hit run. And that big initial problem, that's solved now. Okay. All right. Now, again, you might have a debate on, do I even care about the oscillation that's taking place here? And what that represents is, well, thrust kicks on to actually lift it at t equals 10 seconds, and that our current approach, is allowing I'll say a discrete change in the angular velocity, and that is impossible, and our PID does its best, but it's going to lead to an oscillation. Again, there's a conversation that can be taking place, which is, are we okay with this or not? And you might be, but in general, it is an issue, and people do choose a path like what I'm about to show to deal with it. And so the solution is that, well, just don't ask for such a harsh change. Do not ask for an infinite derivative on your acceleration. And so in the previous video, we talked a little bit about, well, there's position, velocity, acceleration, After that, there's jerk, and then there's snap. And that the solution is, well, let's just set finite constraints on what the jerk and the snap will be in that trajectory. So let's bring up this model. All right. All right. And so I call it the finite snap approach. That's the blue line right there. Both kind of meet the requirement on start off on ground and get to 2,000 meters in a 10-second transition. All right. And I want to show kind of what the acceleration request looks like for this. Okay, so I'll change that selector. I'll delete this one, and I'll bring that down right there. And let's just rerun this. Rescaling the window. And we'll see that the new trajectory is really set by what's, for the most part, square pulse choices on the acceleration. So there's kind of this idea of give me some acceleration that sets position and velocity properly, and or at least gets it going, and then give me a negative pulse to essentially stop that acceleration, right? And these look like square pulses, but if you look close, you'll see there actually is quite a nice, well, there absolutely is a smooth transition. And that's because the approach has been designed to give a smooth transition. So if we go into this block, we'll see that the approach is calculate discrete changes or values for the snap, and then integrate it 4 times, and then gather the acceleration, velocity, and position, and send that into what we've been using to set the trajectory, right? Now, if you look at the measurements, the direct measurements on snap in the upper figure and jerk down here, I think this perhaps shows the method a little bit. And it's a general idea, which we already saw kind of on our acceleration, that square pulse is kind of coupled with a positive and a negative pulse, essentially set, the next, snap down to jerk, the integration of snap to create essentially a trapezoid. And the steepness of the borders on the left and right side, well, that is in a way kind of a measurement of how, I'd just say how you're moving away from kind of the square pulse. But certainly when you look at the whole thing on a time scale like this, these might look a little bit like square pulses. You can see a little bit that they're still trapezoids, but that, as you move to jerk, well, you're again kind of doing the same thing we're doing up here, which is a positive jerk pulse followed by a negative jerk pulse of equal amplitude and magnitude will lead to something that looks kind of like a square pulse on acceleration, right? And so all that's well and good, and all this kind of worked out pretty well. Again, we could undo, get back to our position measurement, run this again. And again, just kind of recall, this is what we got. Now, these are different profiles. And it's not obvious to me that I actually even like the blue one. It looks a little harsher to me. It's such a straight line in the middle, where the gold one's got this nice gradual curve over. But anyways, let's go ahead and try it out, because we know for sure it's not, at the very least, it's not infinite anymore, right? And so what I'm going to do is paste in that trajectory. Okay, and I will hit run. Okay. Again, the model runs pretty quick, but look at that, we still got oscillation. You could argue the frequency is a little bit better. Amplitude almost looks the same to me. But I'd also say somebody probably won't like this, right? And so anyways, let's go and let's just tune it a little bit more. All right. And I'd say this block, which I've been using for at least 10 years at MathWorks, I created it myself, and I just think it's got this nice clean user interface of essentially saying go from this value to this value and take this much time to do it. Well, this one has all kinds of crazy stuff in it. All right. And I came up with terms like, well, snap amplitude makes sense to me. Maximum acceleration, that makes sense to me. But something called jerk couple with, I don't know if that makes sense. Definitely has a clean definition. You can kind of see it in what we were scoping here. Yeah, it's essentially the distance between that pulse and that pulse. All right, but all right, and I'm not going to try to say that this is your permanent solution. It could be, but certainly it could be cleaned up. And what I'm about to do, so I'll kind of show you these parameters right here. It turned out that 100 meters per second to the fourth is actually a really, really high snap. And it really turns out that that's the key parameter that kind of sets how smoothly you transition, from one value of jerk to another, as well as acceleration. It controls all the, I'll call them the downstream, integrals of that. So, so I kind of set this one up with values that are a little bit better chosen. And I brought snap down to 1 meter per second to the fourth. And so I'll just kind of bring this in this way. Hit run. Doesn't that look good? They look very close to me now. And then the accelerations are good to look at too. Let's see if I get this. Okay, and you'll see that all that works out pretty well. All right, so anyways, clearly there's a smooth transition, and we'll take this and we'll paste it back in our other model. So let's delete this, paste this in, and we'll run it one more time. And with that, yeah, I think we're at the very least moving in a good direction. But personally, I'm very pleased by what it looks like now. And we'll save kind of the optimization of the material selections for the propeller to what I think is the more rightful conversation, the more rightful discussion, which is that we're going to always want to reduce the mass of anything that's going to be flying. That's always a good thing. So anyways, but we'll make proper propeller selections in a later video. So thank you.